All right, everybody, welcome to the section 1.2 videos. We are going to be looking at the definite integral in this section, which is this thing that we defined at the end of last week. And with the definite integral, we're going to start thinking about it geometrically and algebraically. Mostly we'll be focusing on the geometry of the situation here. We're going to see a little bit of algebra, but our primary technique for analyzing the integral algebraically is going to come when we get into section 1.3, because we're going to see that the algebra that we have to do right now to compute these actual integrals is pretty complicated, and we don't really want to take that kind of approach every time we're trying to do an integral. So we defined this sequence of symbols last week, and we said that we intended for it to represent the area under the curve of some function. And we defined it using this right-hand side here, where we're looking at this thing was called a Riemann sum, and it was intended to represent a small chunk of the area under the axis. So if we had our axis here and maybe our function f of x here, here's a, here's b, then what we did was we said, well, we want to split up the interval from a to b into a bunch of small rectangles, and we want to take one of those rectangles, which has width delta x, and we want to approximate the area under the curve by, say, picking the right endpoint and taking a small rectangle there, and using that to approximate the area between the left and right endpoint of this little interval here. And the smaller the width of that rectangle, the closer it is to the actual area. So what we said was we want to first add up. That's what this sigma here is doing. It's indicating that we should add up the areas of all of these rectangles. This n here represents the number of rectangles that we had. And we're taking the limit as n goes to infinity because the more rectangles we have, the smaller their widths can be. And the smaller their widths can be, the more accurate the approximation of the area is. So in taking this limit as n goes to infinity, we're continually improving the accuracy of our estimate until we get to the actual area under the curve, which is the end result of this limit. But we should figure out how to both say and write some of these things before we actually go about trying to use them and do computations with them, because it's important to be able to both say and read and interpret these sequences of symbols that we're defining. So we're going to start by saying, how do you read this thing out loud? What words do you use in order to talk about this strange sequence of symbols? So we're going to read this sequence of symbols as the integral from a to b of f of x dx. So that's how we'll read this out loud. The function f of x is called the integrand. So you might remember the word summand from section 1.1. Summands being the things that you're adding up. Here the integrand is the thing that you're integrating. The numbers a and b are going to be called the limits of integration. The variable x is going to be called the variable of integration. And I think that is all of the words that we are going to have to start this section. So we've got a couple of unfamiliar terms here. We've got this thing called the integrand, we've got the limits of integration, and we've got the variable of integration. Great, so let's get a little bit of an intuitive picture here, because we also want to maybe think about we want to try to understand not just this limit process, but maybe we also want a little bit of a picture to understand the actual integral itself and what the symbols are telling us. So note that the following things that I say are not strictly true in a mathematical sense, but they are going to give you a good picture of what the integral means and how we want to think about it. So we'll kind of explain what's going on in this intuitive picture as we walk through it. So the intuitive picture that we want to have here is that we have the graph of some function, and we have, as usual, our x values a and b. And this, we're going to kind of work through this integral symbol from the end back to the front. So we want to think about dx here as being, in some sense, an infinitesimally small width on the x-axis. So for each x value between a and b, we're going to be adding up some rectangle with width dx, and we're going to be using f of x here to represent the height of the rectangle that lies above dx, or that lies above x, with that width dx. So then what the integral sign is telling us to do is it's telling us to add up all of these rectangles, or all of the areas of these rectangles. So we're adding up the areas of these rectangles with height f of x and width dx. So kind of some things that maybe are important to note here is that there are infinitely many of these rectangles. Since there's one for each x value. So I can draw some over kind of each x value here, I can draw some height, and I can create some rectangle with width dx. However, since so you might wonder, well, how can I add up infinitely many numbers and get some finite number? And this is a question that will be answered in a little bit more detail if and when you take Calc 3. But for the moment, we're going to think about the fact that each of these rectangles here essentially, in some sense, has zero area, because we're taking the width of the rectangle to be infinitesimally small. So we're adding up infinitely many of these numbers, but they're all infinitesimally small. And so that's how we're, in some sense, getting some finite number out here. So this is, again, not exactly true. There are no such thing as infinitesimally small numbers, but it's not a bad picture to have in mind, that we're adding up all of these things and they have height exactly equal to the function value and the width exactly equal to some infinitesimally small value, and then we're multiplying those things together, getting some, again, infinitesimally small number, but we're adding up infinitely many of them to get some finite area. So that's maybe a nice way of thinking about this integral.